Right, so chapter 4. Chapter 4 is about atoms and their structure. Studied atoms before. You've studied lots of pieces. Some of you probably mentioned some parts that you knew about for the atom on the bell work. You've studied atoms since what, 5th grade? Yeah, 5th grade is when they do that. So we're going to, our goal here is twofold. One, to figure out how they know about atoms. Okay? How do they know there's atoms? Because no one's ever going to see one. How do they know there's atoms? Okay? And the second fold is to show you how science, we talked about how theories change and how science changes over time. So I want to see how the idea that we have of an atom now is not the original idea, that it's changed over time. And I want to look and see how that science process works in changing those ideas. Okay? Where the ideas come from and how they change over time. So that's two things. So we're going to learn about the atom and learn about how science works. So, the history of the atom. It's a long history, but I'm willing to share it with you. Here is the history of the atom. About 14 billion years ago, there's some debate about that right now. About 14 billion years ago, there was a Big Bang, and atoms were created. That's it. Well, no, actually, there's a little bit more. Every atom made at the Big Bang was hydrogen, and over time, we've made some larger atoms. That's the history of the atom. It's been around since the beginning of the universe. That's not what we're studying. We're not studying the history of the atom. We're studying the idea of the atom. We're talking about the atom in your head, not the atom in the world. Okay? Because in truth, atoms really only exist in your head. They're just a theory that explains everything they've ever seen. And as they see more, that theory gets better. Does that make sense? So we're going to talk about where the idea of the atom came from and why it was slow to be accepted. And then how they finally came to the conclusion that there was atoms. Okay, the original idea came out of ancient Greece. About 400 BC. BCE, before current era. Okay. Now, to you it looks like a random date, but once you study more history, you'll figure out that 400 BC Greece is the peak of Athens. Athens is at its power. When they talk about all the great things the Greeks did, developing democracy, coming up with philosophy, doing all the math, 400 BC is when it reached its apex. Okay? So that was the golden age of Greece. And then during that time, there were a couple of people that most textbooks only give Democritus credit. Some textbooks give Leucippus credit. And the reason why they get credit is because they were the heads of their schools of philosophy. There was different philosophies in ancient Greece. Some believed the universe worked this way, some believed it worked that way. And they were the head of the school that believed that the universe worked by moving little pieces around. That was the pieces that was important. How many had ever heard of Democritus before you read last night? That's not surprising. Okay. But they weren't around. But this is what they did. Now, they were philosophers, not scientists. I wrote philosopher on purpose because science hadn't been invented yet. That idea of testing the world, to come up with a hypothesis and then testing it with an experiment, was the exact opposite of what they did in ancient Greece. In ancient Greece, they believed that the world would lie to you. That truth and perfection came out of logic and argument. Reasoning gave you the truth. The world lies to you. Okay? So they did not have scientists. They had philosophers. And this is what philosophers get to do. Philosophers get to say, hey, look, there's a beach. How do I make a beach? I can make a huge, miles-long beach out of little tiny pieces of sand. Okay? Everybody comfortable with that? And if I take one of those pieces of sand and crush it or cut it, what I get is smaller pieces of sand. So what makes up sand? Smaller pieces of sand. So far, this is what they've experienced. Now they're going to do what philosophers get to do. It's a pretty easy job. You get to ask yourself a question and then answer it. You pick the question, you pick the answer. So they said, is there a smallest piece of sand so small that if you cut it, you no longer have sand? Seems like a logical question, right? If I cut sand, I get sand. How far can I cut it? Can I cut it forever, or am I going to reach a spot where I can't cut it and still have sand? That's the question they asked. And being philosophers, not scientists, they said there must be. And they called that piece by the Greek word that meant not to be cut. The root word for cut is tome. You put the A in front of it, means the opposite, right? So a, tome, not cut. It translates literally to are indivisible. Divisible means it can be cut. In means it can't. So the tome is like divisible, cuttable. The A is can't. So that's where they got the word, not to be cut. That's where the word atoms came from. But you hadn't heard about Democritus and Leucippus. There was another Greek around. Same time. There's lots of Greeks, but there's another one. You may have heard of this one. Aristotle. Probably heard his name before. He's famous. We'll talk about why he got famous and what it has to do with what we're teaching. Now, Aristotle disagreed with Democritus and Leucippus because he was the head of a different school of philosophy. His philosophy school said everything was continuous, that there's a whole wide range of things, a whole spectrum of possibilities. But he said that the universe is made up of 4 elements. 4. Everything in the universe is made up of 4 things. Okay, so not the elements we know. His 4 elements were fire. If things were made of the element fire, they were hot. They were shiny. If they were made up of air, they were light. If they were made of the element earth, they were cool and heavy. Water made things liquid, also was on the cool side. And those 4 elements made everything in the universe. You just blended them in different ways. So what we call boiling water, Aristotle would have said, you're taking the element water and you're adding fire and air to it and making this completely new thing called steam. That steam is the elements fire and water, or fire, water, and air mixed together. And that's how they thought everything was made. That you just blended them in a different proportion to make something else different. So you can blend them in different proportions, so that's all the proportions are possible, the continuousness. Because you can mix them in any proportion. Which disagrees with Democritus, because Democritus says you've got pieces. And if I got pieces, I don't have continuous. I got to have whole chunks. The numbers have to jump. Because there's nothing in between 1 piece and 2 pieces. You're not going to have 1.5 pieces. You've got to have whole pieces. So the whole pieces of Democritus disagreed with the blending of Aristotle. And actually, the whole philosophies clashed. This is just one example of where they clashed. Who was right? The answer is neither one of them. But more importantly, how did the Greeks decide who was right? Okay, because they didn't experiment. They didn't trust the word. They didn't trust the world. That you got to the truth through logic and reasoning. That your answer had to be logical. That's how you got to the truth. The world will lie to you, but logic gets you there. So the way you test logic is by debating, by arguing with each other. Okay? It was a very formalized system of debate called the rhetoric. And that's what you did in ancient Greece for fun, is you went and watched the philosophers argue. There wasn't a lot of TV then. Well, any. So you'd go to the amphitheater and these people would be arguing about who was right about how the world worked. So now we get back to, we got two competing ideas. Which one have you heard of the person before? Aristotle, right? He won. And he won not just about elements versus particles. He won about his whole philosophy was picked up, and Democritus' philosophy, the particle one, went away. That continuous philosophy of Aristotle was picked up. And most importantly, it was picked up and integrated into the early Christian church in Greece. So the early Christian church picked up Aristotle's philosophy. And along the way, picked up Aristotle's view of the world. And so his ideas lasted from then until through the Middle Ages. In fact, there's a long time that if you said that Aristotle was wrong, you were a heretic and could be burned at the stake. Aristotle was right because the church picked him up. Okay? Even though he wasn't Christian, because he was in 400 BC. But disagreeing with him was heresy. Okay? The people you see that led to chemistry, you see people doing things that look like chemistry. Got things bubbling in glass and pouring the stuff around, but they're not doing chemistry because they're not doing science. They have logically figured out what's supposed to happen, so they're just going to make it happen, which is the opposite of science. Science says, hey, let's see what happens when I do this. Alchemy says, I can do this. Let me do it. So when I picture an alchemist, I picture Merlin from King Arthur's court. In his little place, got all the fuming bottles and all that stuff. And one of the things they're famous for is trying to change lead into gold. Okay? Makes them sound crazy, right? But they weren't crazy. These were the smartest people around. Smartest people of their era. And if Aristotle is right, you should be able to turn lead into gold. Because lead is dense. And it's a dark gray. So lead is almost all element earth. Okay? Gold is dense as well. So it's got lots of earth. But it's also shiny and yellow. So it's got some fire in it. So if you can just get the fire to stick to the lead, it should turn it into gold. Because you're putting earth and fire together, and earth and fire make gold. Because gold's got a lot of earth and fire. They're not crazy. If Aristotle was right about the way the world works, you should be able to turn lead into gold. He was wrong about the way the world worked. So he never got there. But they weren't crazy. They weren't stupid. They were the smartest people of their era. They just couldn't do what was impossible. Because they had the wrong philosophy. They had the wrong philosophy behind what they were doing. It wasn't science. Okay, so who's next? Yeah, they came up with Democritus came up with the idea, and then they lost the argument, and the idea of atoms went away all the way through the Middle Ages. So who's next on the list? Well, in your book, the next person is John Dalton, which is late 1700s. That means during the American Revolution, to give you a sense of scale. Okay. Now, your book talks about him as a teacher, but you have to remember what a teacher was in the late 1700s. There weren't schools. A teacher was more of a tutor that a family or several families would hire somebody to teach their kids. If you only had one kid, you'd go with another family so that you get your money's worth. But they hired somebody to come teach your family. There was no public schools. If you wanted your kids taught, you had to pay somebody to do it, and we did it locally. Okay. Now, the late 1700s is important for a couple of reasons. First, the reason why he could summarize the experiments of others was because they had good mail. That Dalton could mail somebody in Italy and expect the letter to get there, and he could expect a reply. He had reliable mail all the way across Europe, so that scientists could talk to each other. The printing press had been invented, so you could distribute your work. You could make books of your science. Okay. What he was interested in was the lab results from other people, and the lab results he was looking at was what happens when you tear down an element, or tear down a compound and get elements. Because along the way, they had changed the definition of element. In the late 1600s, they came up with a new definition of element based on experimenting, because science got invented in the late 1600s. People finally realized, hey, if you want to know how about the world works, you should look at the world and try doing things to the world and see what happens. Which is not what Greeks did. Greeks up to that point, you said, look in your head and try to make the world do what your head says. Where science says, look what the world does, and in your head, figure out what's going on. See that switch? That's the switch between Aristotle, I'm right, the world's wrong, versus the world will tell me about how it's right. So they changed the definition of element. Element is now something that can't be made any simpler. So the way you would find an element was you would take something that you didn't know what it was, and you would heat it, put electricity through it, do some chemical change to tear it into pieces. And if you knew what that piece was, what it was made of, it was completely uninteresting and you threw it away. If you got a piece you don't know what it is, you try to tear it apart. If it tears apart and you know what the pieces are, you throw them away. If you don't know what the pieces are, you got something you don't know what it is, try to tear it apart. And when you finally get to something you can't tear apart anymore, then it's an element. That's how you define elements, by tearing atoms away, tearing stuff away from each other. Okay? So that's the data that Dalton was using to come up with his ideas. Was chemists all over the world were tearing things apart into their elements, and he was looking at what they fell apart into. Okay. He combined them in Dalton's atomic theory. Okay. So he didn't come up with the theory first. The theory doesn't start this. What comes up first is he noticed patterns in the data. Okay? He noticed the law of conservation of mass. You guys have heard of that before, right? What's the law of conservation of mass? Okay, to conserve something means to save it, right? Well, to a scientist, conservation means perfect, that everything's saved. Law of conservation of mass is that whatever weight you start with, you finish with. That if you weighed something at the start of a change and you weighed it at the end it would weigh the same. Fact is, every time he looked at all these people's data, and what he looked at was, this is how heavy it was when it started, this is how heavy the two pieces were, the two pieces added up to what the original was. No matter where they did it, he saw those numbers. Okay? So the law of conservation of mass, he saw patterns in the numbers. And he had to try to explain those patterns. I'll talk about a couple other patterns he saw and how he had to explain them. But what he did was he took the idea of atoms from Democritus and combined it with the idea of elements as simplest things that can't be broken down. With a new idea of element that he combined it. Not with Aristotle's old fire, earth, water, and air, but with those new elements they'd found. So, atoms are an explanation. Okay? Atoms are an explanation. Atoms are a theory. They explain why these things happen. So, atoms are going to explain why mass is conserved. He knew mass was conserved. Why? His explanation was atoms. So, here's what his atomic theory is called. Here's the argument. So Dalton's atomic theory, usually broken down into 4 separate little pieces, all interrelated. Statement number 1. Everything is made up of little tiny pieces called atoms. So matter means stuff. So anything in the solid, liquid, or gas is made up of tiny indivisible, not invisible, indivisible. In, prefix a means in, and remember the Greek word for cuts was atom. Okay? That's where they got the word. So he used Democritus' word because it describes, can't be cut. Okay? Atoms of the same element are identical. Those of different atoms are different. Those of different elements are different. Sorry, I should say elements here. The same elements are the same, different elements are different. That there are atoms of hydrogen, and every hydrogen atom is like every other hydrogen atom. There are atoms of oxygen, and every oxygen atom is like every other oxygen atom. But every oxygen atom is different than every hydrogen atom. Just with those 2 statements, he's explaining why. This explains why there's elements. Why is there a simplest kind of matter? Why, when I break things down, do I get to something I can't break down and make any simpler? Because when I start off, I got multiple kinds of atoms. As I tear it apart, I'm getting rid of the atoms I know and leaving the atoms I don't know. And when I can't tear it apart anymore, I have just the atoms I don't know. So those 2 statements explain why there's elements. Because everything's made up of little pieces, and different elements have different kinds of pieces. See how atoms are an explanation. They explain why there's elements. Atoms of different elements combine in whole number ratios to form compounds.
Are you there?
Mr. Green? Yeah. She's going to lunch. No, okay. No, that's fine. I'll send her. Okay, bye-bye. Okay, so now we know there's different elements, and what makes an element different from another is a different kind of atom. Now if I combine those atoms, I can make compounds because there's more things in the world than there are elements. So I've got to be able to put those atoms together to make new stuff. That a chemical reaction is putting together atoms or taking atoms apart. And chemical reactions involve the rearrangement of atoms. No new atoms are created or destroyed. So the first two explained why there were elements. The next two explained, or the last one explained conservation of mass. The reason why they weigh the same at the beginning and the end is because every single atom is there. Every atom I start with, I end with. And since atoms weigh a certain amount, they're going to weigh the same at the beginning and the end. Atoms explain why things happen the way they do. Atoms are an explanation. Atoms are a theory. Okay. But how do they know number 3? How do they know that they combined in whole number ratios? Because you can't have parts and pieces. But what evidence did they have that they didn't never get parts and pieces? Because if I take the pieces and crack them in half, they're still going to weigh the same on the other side. Right? Okay. Actually, it turned into, it's about not more about division, but it's more about building. Okay. And he had actually, before we get to this point, what helped him come up with this idea was a couple of other laws. One is the law of definite proportion. That number 3 is, it explains number 3 on Dalton's atomic theory. It explains how they know they combine in whole number ratios. So it's another law, another pattern they saw in what happened. And the pattern they saw was a definite proportion. Definite meaning certain, proportion meaning ratio. A law of certain ratio. That every compound has a specific ratio of elements. That when he's looking at everybody's examples where they were telling things apart, no matter who tore the water apart, or how much water they tore apart, or where they got the water from that they tore apart, the oxygen was always 8 times heavier than the hydrogen. No matter where you get water, no matter how much water you have, in that water, the oxygen weighs 8 times what the hydrogen weighs. So it's a ratio by mass. You look at the mass. So if it's not 8 parts oxygen to 1 part hydrogen, it's not water. No matter where you get the water from, no matter how much water you have, or if you're making water, you're going to use 8 times the mass of oxygen than you do hydrogen when you put it together and go the other direction. They always combined in a certain ratio. He saw that pattern in everybody's data. Make sense? That's what we mean by laws. So he wanted to know why. Why is there a definite ratio? Well, because you've got to combine all atoms. Combine atoms that weigh different. O atoms 8 times heavier than H. That's how he would explain it. The reason why the oxygen is 8 times heavier than the hydrogen is every oxygen atom is 8 times heavier than every hydrogen atom. And since I put those together to make water, no matter how much water I make, I'm always putting, oxygen is always going to weigh 8 times what the hydrogen is. But he was wrong. He thought there was only 1 hydrogen atom at the time. He didn't know there was 2 in water. But he just came up with the idea of atoms, so the fact that he knew that it was adding in pieces. Whole pieces. Okay? So that says, well, that makes sense, but it's not quite proof. Okay? It's not quite proof because I could be splitting pieces along the way. The real piece came. The real evidence. The real evidence came with a different law. Okay? The law of multiple proportions. Okay, I'm going to write this on the screen, and what I write is actually what it is, but it's horrible to understand. I hate to teach this law just because the wording is awful. Because multiple proportion means more than one ratio, that you take a ratio of the ratios. So first of all, you have to have elements that make more than one compound. So hydrogen and oxygen don't just make water, they also make hydrogen peroxide. So you got to have that kind of situation. Two elements that make more than one compound. And then, right here, the thing I got in parentheses, that is the law of definite proportion. That's the pieces in the law of definite proportion. The amount of ratio of the second element that combines with 1 gram of the first element. That is, the hydrogen weighs 8 times as much as, the oxygen weighs 8 times as much as the hydrogen in water. That's the ratio. I've got to make that same ratio for hydrogen peroxide. So if I find the ratio for the first compound and I find the ratio for the second compound, then I take a ratio of those ratios. And when I get that ratio, it's a small whole number. The ratio of the ratios is a whole number ratio. The ratios of the ratios is a whole number ratio. Okay. So we said water was 8 grams of oxygen per gram of hydrogen, right? Well, hydrogen peroxide is 16 to 1. So I found the ratio in water, and I found the ratio in hydrogen peroxide. They did this by tearing them apart into elements. And if you divide the 16 by the 8, you get 2 to 1. And he found that no matter what compounds, it was always a whole number ratio when you compared two compounds. That the weights always jumped by a whole number. And that's what told him there was atoms. Because the only explanation for why the weights would jump from one compound to the next is you have to add a whole atom. So the weight is not going to go steadily increase. It's going to go, I go up by 8, and then I add another oxygen, I add 8 more. Then I add another oxygen, I add an 8 more. So I'm going to always get whole number jumps when I do that. Why don't you go to guidance instead of going to your next class? Mr. Stites wanted to see you.
Please report to guidance. Jacob, Corbin, please report to guidance.
All right. Have a good weekend. And that's how they know there's atoms.